All right. Yeah, let's enter the last segment of this conference. And I'd like to just welcome Andy with a lightning talk on kernel bottlenecks.
So we go straight to the point. This is a relevant part of the profiler output for an application. It's a heterogeneous application in the sense that part is performed on GPU, this part. No pointer. Basically, this part, main, is performed on GPU. Then we have two steps, finalize and step, and some mysterious step that are performed on the CPU. In case you wonder, it's all about polynomial arithmetic, things like discrete Fourier transform over 32 one-bit ring. In this case, ring is basically just a set that is defined by modular arithmetics. And in this case, we are looking at 100 polynomials of degree 2 raised to 18th. And this is not smallest application. There are applications that are kind of using 227 and larger rings, like 256-bit rings, and those are kind of even more fun. Well, I mean, since those are more computationally intensive, the ratio between GPU and CPU is completely different. But in this case, this is case tailored specifically for kind of this presentation. So that for simplicity, we just break it down, round up, and break it down to 4 steps. On GPU is like 40 milliseconds. Then there are 2 steps, 20 milliseconds each on CPU. And then there is a mysterious step that I didn't mark yet. I mean, basically, it doesn't matter what the steps are. All you need to follow is just the timings as it progresses through the presentation. So, how many think that Rust is best thin since sliced bread? None? Oh dear, this is unexpected. Yeah, but I mean, normally Rust programmers, they think that. Point is that this is, sorry? There is some truth. Right. Point is that this application is written in Rust, and the mysterious step is basically, it takes 70 milliseconds.
So Rust is the worst.
No, I mean the whole application. I mean, 20 milliseconds is kind of Rust as well. Point, and kind of what I'm about to say is not really a kind of Rust specific. So 70 milliseconds is just memset. So what's up with that? I mean, it amounts to 2 gigabytes per second rate. How does it compare to PCI, for example, 4 lanes? I mean, GPU, I mean, not kind of top-notch GPU is usually like 4-lane PCI 4. So how fast is that? Anybody remembers? It's like 32 gigabytes a second. So this is small portion. And this is just memset. And kind of why is it important in the context of Rust is that the first thing you know about Rust is that memory-safe language. Compiler has to kind of have the ultimate control over kind of initialization. I mean, everything should be initialized. Everything should be created with the default constructor at least. And there you have it. So this is, of course, totally unacceptable. So any ways to solve it so that we have to step out the kind of Rust mindset and do something else? Of course. But I mean, actually, C++ won't give you kind of advantage here. You will still kind of have to grapple with this problem. It's just the C++ users will come to the solution way faster, or at least seek out for the solution. Rust users will just sit there forever and never kind of go out. So any suggestions? No, first of all, why so slow? Basically, what happens when you allocate new memory, what happens is that you simply declare an intent to use it. The memory is not wired. So what's going on is that you start going and start wiring pages one by one. As you progress to the mem set, there will be, at each 4 kilobyte, there will be page fault that will be served by the kernel, and then you are back, and that's why you end up with a 2 gigabyte. To be fair, 2 gigabyte is for this specific system. I mean, you will be able to kind of get better, you can get better numbers on different systems. For example, on my desktop, I had in the same situation like 6 gigabyte per second. Still way too low for the kind of to keep up with, for example, PCI, and still unacceptable. But this is a highly system-specific kind of value, and but I mean, you still have to solve it. So, first thing that comes to mind, larger page sizes, right? So we take over Rust allocation, do mmap with the larger page sizes, 2 megabyte page sizes, and let it run its course. So it goes down to 15 milliseconds. So this is good, but then we recall that actually when you do a kind of anonymous mmap, it's guaranteed to return 0 pages. So why the hell do we kind of want to double zero it? So we just do it, but I mean, all of a sudden, that 15 milliseconds that we have won moved to the second step. So that's because kind of the second step kind of have to go through the memory and initialize it at its own pace, so that we didn't win anything. But if we go back to the 4 kilobyte pages and no init, I mean, as you can see, the initialization stage is now 0 milliseconds, so it's very good win. If only we could get it. All of a sudden, kind of all the gain is moved to the GPU side. How come? And the reason for that is that that part, the green bars, these are copies from the host to the memory. And it just so happens in this particular application, the thing is that it doesn't initialize the whole memory. It's quite sparse, so that there are quite a lot of pages, 4 kilobyte pages that are not touched at all. And why it was slow with 2 megabyte pages? Because the probability that you hit page is very high. And apparently you hit all the pages. And is there anything one can do in this case? No ideas? Okay. Sorry? No, doesn't help. So we just touch pages in background. That is, as we start this first calculational step, we also just start touching pages in background, so that all the pages that are, by the time we get to the mem copy, all the pages are kind of wired, and so that mem copy goes at the usual rate. And just in case you wonder, why do I kind of kept this 20 millisecond step in the middle? We're just so lucky to have it, actually. Because if we didn't have it, the background touch wouldn't be able to kind of be ready in time, so that it would be punished on the GPU side. Or rather, on GPU, not on GPU side, but on the GPU part of the calculation. And with this in mind, just as a fun fact, not relevant to this representation, but also taken out of kind of Rust programmer mindset, and by kind of re-implemented the synchronization and parallelization, we were able to cut the 20 milliseconds to less than 3. So that's about kind of core of the presentation. So now I have a pop quiz for Linux users. So we do malloc, memset, as we already established, it's like 2 gigabytes a second on that particular system. We do free, then malloc, then memset again. How many believe that it would be fast? How many believe that it would be fast? I mean, how fast the second memset? Nobody?
You're probably on master pages, right? Yes. I mean, big enough.
Sorry?
It's a big allocation. You're probably on master pages, and then you take the cost again. Probably. Haven't tested.
I would say so as well. Yeah. Exactly.
Your slide is
But it's user space, right?
Right. Same question for OpenBSD. Or for FreeBSD, sorry. If I stepped on any toes. Or NetBSD. Or, sorry. As I said, sorry if I stepped on any toes.
But it's either the same or different. It's one of those.
Let's fall for the same.
Okay.
There are actually a few tunable parameters for the libc, so that one can kind of make it work. Linux or glibc, one can kind of make it work approximately the same way as BSD by default. And one can either set like few environment variables, or one can just make some call in the very beginning and kind of be done with that. So, why I'm telling this story? Basically, the twofold reason. This is kind of not Rust specific in the sense that it's not like Rust users are the only ones that are prone to kind of these kind of pitfalls. I mean, one can end up in the same situation even with C and C++. And second, it's kind of plea in the sense that if you find yourself in position to do something about page wiring rate, please do so. I mean, one idea could be that one can batch them in the sense that if you have large map, maybe you can kind of wire like, say, 16 pages at a time so that there will be less faults or transitions from the user land to the kernel and back. Fun fact in the context. For example, Apple Silicon, that is ARM hardware, kind of have a reputation of being fast, right? One of the reasons is that the default page size is 16 kilobytes instead of 4. So that they actually kind of do a better job in amortizing the kind of costs of allocating the memory.
Raspberry Pi 5 does that too.
Sorry?
Raspberry Pi 5 does that too. It skips those.
Okay. Okay, that's about it.
All right.
Any
Thanks.
questions?
Interesting hacks.
Any questions? No? Okay.
Okay. I think Ian is up next with something he wants to show.
I went to plumbers in Vienna and I talked to some people, and one of them was acquaintance or friend of Toke, and then we talked some more. And he pointed me to a small project called ARPSponge. Because when you have a cloud environment connected to the internet where all your IP addresses are not used all the time, you have a very annoying ARP amplification kind of thing going on. Because, yes? Because everybody scans you all the time, and so for all the 65K TCP port, all the 65K UDP ports, plus the switch goes, No one responded. I'll try 5 more times. And if no one responds, this is just very annoying. So,
We make it bigger.
yeah, it will happen. Because I need to read as well. Sorry. And we have the original ARP sponge here, but I didn't really want to use that one because it was very limited for my use case. And since the original ARP sponge was AKA Bob, I named mine Bobby. And this will now be running, and it will report back how many ARP responses it does, how many ARP requests it sees for 5 seconds, or per second, and how many responses it sends for that time amount. And also reports back the size of the hash tree of all the hosts it sees. So it was an interesting hack because we have had, like Jesper and Toke has also been presenting XDP. So I implemented this in XDP where the client part that reads all the network traffic is done in XDP, but the part that sends the responses back is just done normally. So this is the thing I did. It is usually running in production. It's been off now for a while just to see how many ARP requests you see per second, and the aim of this game is to see that go down significantly. And that was basically it. Yeah. Exactly. No, well, I mean, if there's any questions on this, feel free. But it's this was just the thing that I did. And it's very valuable to us because ARP traffic is never going away. Apparently the neighbor protocol is better than the ARP protocol. So no, I haven't looked at that yet. So we do have the IPv6 endpoint now as well. Thank you, Toke. And that one is not as noticeable.
But do you just reply that the ARP is okay?
I basically do ARP cache poisoning.
Yeah.
Freely. I just respond and say, I'm over here, and it goes down. And the fun thing is that any VM that starts up, that starts using an IP address, will do a RARP and announce itself, and then this will just disappear. So it's just a great benefit for us, and no one else cares really, but we needed a talk. This is how this started. The code. That is why I left one half empty. And I don't usually actually use Firefox, but it's over there. Yeah, on GitHub. I don't know if that can be seen. Basically, search for ARP sponge TNG, and you will find it. I do a little bit, so the original code basically hard-coded did 5,000 retries, and we will block you or fake you. Mine is just implementing a simple leaky bucket to respond to all the biggest talkers as soon as possible, with still like a little bit of latency before it actually starts responding. So if someone wants to play with it, feel free. This was my little project after Vienna. Any questions? Also, observe. Good. Yeah, well, I mean, it's bursty.
It's broken.
Yeah. No, it's not broken. It's bursty. It handles bursts. So that.
Where are you running this?
So it's running in what we call ERDC. So it's a cloud environment that we run across the motorway. That way. Apparently. So we have a cloud environment for research corporations and so on in Sweden and abroad. So this is just because the internet is a bad place, and even Ericsson Security is a bad actor in this case. But we're doing what we can to limit all the traffic that goes. I mean, the problem with this is as you go up in size, you have multiple switches. So it's not like you just see this on one machine. You see it on like A few hundred machines get all of these things, basically. So it's just a way of short-circuiting it to remove it. Older switches on the same series that we have in this case actually had a thing where you could say cache a negative, but it's not available anymore for some reason.
Why not routing segments?
What?
Why not routing segments?
This is L2. What are you going to route?
Yeah, what kind?
Yeah.
Segment all the machines.
So I have one subnet per machine.
Stop having big L2 domains.
Yeah, but it's still, it's not really possible for a cloud environment to have small L2 domains. Because this is the endpoint of the route for the machines. That is the route.
You run thousands of machines?
A few hundred anyway. It's like 300 machines plus. With like 2,048 IP addresses.
You run back protocols, all of them.
Yeah, you get BGP per VM. So.
But do you need to couple learning in this setup?
The what?
Do you need to couple learning? Wouldn't the L2 starting forward with what learning?
So the problem is that you don't know which IP address will have this, which MAC address in the future. Because an IP address is just floating.
But you said that these are dynamic machines, so you could fake even the MAC address that corresponds to that virtual machine, right?
Yes, they are faked, out of my control. From a perspective of the networking, you'll have a network namespace that goes into a Linux virtual switch that goes into Open vSwitch. Then the VXLANs over to a vSwitch that goes to a Linux bridge that then goes to an interface that has a MAC address. So it's out of our control. So this is just a way to limit the amount of ARP floods we have. And I mean, I turned this off Monday, and my colleague was at me just a few days ago. Oh, sorry, last Monday. And my colleague was at me during the weekend, almost going like, "There's too much traffic." It's just it's a few megabits, but it's still like there's quite a high PPS. So.
Yeah, whenever you run machines on the same L2 domain, you trust them not to screw with them.
Yeah.
Because it can trivially take over any IP in that segment.
Yes. And the amount of traffic you get from the internet for just people going like, "Oh, this is something fun to exploit." Yeah. Anyway, that was it. If there's no more questions. There's more questions.
Who's Bobby?
So I said this before.
Oh, sorry.
So ARP-Sponge, the original project is implemented in Perl. It only handled one subnet per interface, which I found annoying in my case. So I chose to redo it in C, because that's my language of preference, and also to learn more about XDP and eBPF. So when I re-implemented it as an homage to the original project that they call themselves, AKA Bob, I said ARP-Sponge TNG, AKA Bobby. Yes.
I apologize for a redundant question.
It's okay. It was a clearer explanation as well. So my preparation for this talk has been none. Any other questions? Not really, I think. Or no?
No, thank you. And we have Robert. There you are. He's going to give us an update about ELISA.
I will talk about the workshop we had in Lund 2 weeks ago, hosted by Volvo Cars and me in particular. And I'm also curious, how many of here knows what ELISA is? Okay. Yeah. So half of you will get more enlightened, and the other will be really enlightened. So this will be an interesting session. The reason I, from Volvo Cars, try to engage in these kind of communities is because of this. You can ignore open source, but you cannot ignore the consequence of ignoring open source. And classic automotive has a challenge, a huge challenge of living in the proprietary world and believe I can do it much better myself. Everything. It's a fallacy. It has worked so far. And in order to open source being able to be used in automotive, We need to think outside of where we have been before. AutoSAR, Tier 1s, microcontrollers, and so on. This is actually a quote from Ayn Rand, which was about you can ignore reality, but you cannot ignore the consequences of reality. But I thought open source applies to it. For me, that's reality. This was the ingress, and these were the people that showed up. It's a distinguished list of people, including Kate Stewart came. For those of you who don't know her, I call her Miss Linux Foundation. She's very active there. And literally all the, call it maintainers or workshop leaders within ELISA. And now comes the educational part. What does ELISA do? It enables Linux to be used in safety applications. It could be medical, it could be automotive, it could be trains, nuclear power plants, now lately even space. And how a Linux system can be utilized there and still be safe. Whatever safety is, I won't go through safety here. I've done it before. Look at my old presentations then. But it's a way of thinking and doing stuff where open source and Linux in particular, but not limited to, can be used in what we would call safety critical systems. But it doesn't provide a safe Linux out of the box, just insert in the car. Just like CRA doesn't just get solved by each community. It's up to the OEM or the main final integrator of everything to make sure these things are safe. And I just thought I'd put this slide up. It's from Philip Arman. He's from Bosch ETAS, has put together a good presentation. I have the link there. I will share this later. You can look at it. This is ELISA project's definition of what they are doing. And most importantly here is the collaboration with other projects. In this case, he mentions Zen, Zephyr, SPDX, Yocto, AGL, automotive grade Linux. But it's even more. Rust Consortium starts to enter there, and more are interested, Eclipse Foundation and so on. They have a few work groups, aerospace, automotive, features, architecture, a lot of process thinking work here, but that's what's needed here. How do we handle the traceability or the assurance of safety, the evidence, when we are working within an open source code base, so to say? All of these people, Paul Arbatella from CodeThink, Gabriel Palono, Red Hat, Philip Arman, Bosch, even the Boeing guys were there, but they called in uncomfortable hours to be part of this workshop. And lately, if you haven't noticed, there is also a space-grade Linux, special interest group. And in December 10 to 12, they had this first workshop at the NASA premises. And I called in on uncomfortable hours. And it was extremely interesting to see the challenges the space industry has. And there's a lot of Linux there. SpaceX rockets are based on Linux. Satellites are based on Linux. And I learned something that was so interesting, I had to share it. If you are not familiar with the South Atlantic anomaly, they showed us that the radiation level in space is so high in a small area outside of South America in the Atlantics. It has to do with magnets and radiation dips, that their error correction things in Linux kicked off very often there. So as soon as a satellite passes over that blue region of the Earth here, you will have a lot of bit flips. But they handle it. They've written stuff and codes to manage and deal with all these radiation efforts. And Ingenuity to the left from your side is a Qualcomm Snapdragon running Linux. Seems to work on Mars at least. So it's safe there. It won't hurt anybody, we think. Or some alien will come and hunt us, you know. You've destroyed my garden gnome. Yeah, so this is actually an interesting... Sure, just interrupt.
Is that static, that anomaly, or does it drift?
It's actually static, they noticed. It has to do with where the poles are, where the Yeah, perhaps it moves, but it's a pretty big patch. I suggest you read up on the Wikipedia link about it instead of asking me, because I'm absolutely not an expert on it. But they noticed it by just looking at the logs on their Linux satellites. It was still interesting to hear. There are a lot of companies involved in as members, but most importantly, it's the interaction with others. S-Core, which is mentioned on the top, is actually an Eclipse SDV project. It's an attempt to make an open source automotive software platform. And the Kernel CI team, are you familiar with Kernel CI and the Linux Foundation? They are looking at things for automated testing CI, reproducibility or whatever, is an important part of this ELISA project, since building in a predictable way is very important. They're also involved in SPDX and increasing it with profiles. I will come to that later. And there has been interesting interaction with LLVM and StressNG. Of course, you need to have more tests, more validation. And in LLVM, it was about code coverage with a certain flag. You can compile your code, and then you can run it. You run your tests, and you get numbers of code coverage of each of your whatever you built. It's actually in the progress of being something, but it has potential. And the workshop looked something like this. If you're interested, you can look it up on the internet as well. We had our usual spot. I think some of you, Jesper, you were there last year. Not sure how many attended more last year, but this year I think you were there, Nico. I was there, and what did you think of it, Nico? It was great. It was a good bunch of people open-heartedly discussing the challenges when it comes to safety and make things safe, but not just by documentation, but also by code. And that's just an interesting thing. A guy who showed up and surprised us in this event was actually David Cortelis, Mr. Arduino. He just happened to invent it. And also, he just happens to live in Malmö. And he has his factory out in the bush somewhere. It was a pleasant to listen to what he has to say, and he thinks about using Arduinos in more safety appliances as well. We had a dinner at Stacket. For those who had the speakers dinner, might recognize the place. We had more days where we discussed a little bit deeper into what safety is about. And my conclusion is, well, you need to understand what you're doing, okay? So open source communities, they won't help you. What they will help you is that if you understand your system sufficiently, there are tools, methods, and ways of working. And the thing I wanted to emphasize here is also the SPDX evolution. It has grown way beyond software bill of material license compliance. And Nicole Papler and Kate were the ones presenting with this a lot. And it turns out that today, a lot of safety information, in this case, it could be requirements mapped towards results, towards your claims, whatever you make. That's an Excel sheet, a Word document, Lotus Notes document. You know, it's so obsoleted. And I got really scared when I see it, that this is what you call safety. I can do much better. Git log is better than what you have. So SPDX is an information exchange format, which will be growing with safety extensions, where you deploy software, deploy SBOOMs, design SBOOM, runtime SBOOM. It's a lot of profiles that are entering. And in 3.1, which will come later, I think it will be realized. And security is there as well. You talked about it. It's growing. And if you can automate this in your CI and make it part of your build tool chain, you get a lot of evidence and knowledge about what you have built, what's included, which tests passed, how are the results, because you need to continuously build huge source code bases. And you can't rely on somebody finding an Excel sheet somewhere, which build to which what, how, when. So this is actually mandatory. This will be big and important, I think. Håkan from Volvo Cars presented how we run it at Volvo. There is still a way to go, but it's getting there. We had pizzas. Philip Arman made this QR code when we ordered. It was fun, barely worked, but we got pizzas. We were on the rooftop having fun. And there was a third day. People were tired. But it was a good conference. I think it's very important to meet like this. And I still appreciate that we hosted it for the second time in Lund. And probably because Kate was very happy to leave US for a while. And a lot of Europeans felt more comfortable being in Europe than traveling to the US. So it had a thing to do with that. So yeah, this is a wrap up. I think this is what we should bring with us. And for Ian, this is the reaction from everyone. I must have it. So yeah, I'm done. Thank you.